All right, so today we're going to dive into something called kinematics. Now, I know, it sounds kind of fancy, but really it's just the science of how things move. Everything from a sprinter blasting out of the blocks to a planet orbiting the sun. So let's get right into it and see how we can talk about all this motion with like pinpoint precision.
All right, think about it for a second. Motion is everywhere, right? You see it every single day. A car driving down the street, a ball flying through the air, even just you walking from one room to another. But if you had to scientifically describe that motion, how would you actually do it? Yeah, it's saying something like, it went over there pretty fast. Well, that's just not going to cut it in the world of physics.
And to get that kind of precision, we need to learn a special vocabulary. The best way to think about kinematics is as the language of motion. It gives us the tools, the actual words, to go from just kind of guessing to making exact calculations and even predictions. And just like with any new language, you've got to start with the basics.
Okay, so let's start building that vocabulary. We're going to go through the absolute bedrock concepts you need to speak this language of motion fluently. Now, some of these might seem really simple at first, but trust me, the little differences between them, they are so important.
First up, we've got distance. This is the one you're probably super familiar with. It's really simple. It's the total ground an object covers, period. So if you walk, say, 10 steps forward and then 5 steps back, your total distance is 15 steps. Easy, right? It's like the odometer on your car. It tracks the entire path, all the twists, all the turns.
Okay, now let's contrast that with displacement. See, displacement couldn't care less about the path you took. All it cares about is the straight line between where you started and where you ended up. It's that as the crow flies distance. And here's the really critical part, displacement always includes direction.
This next example just nails the difference between the two. Picture a runner on a standard 400-meter track. They do one full lap. What's the distance they've covered? Well, obviously it's 400 meters, but what's their displacement? It's zero, a big fat zero. Why? Because they ended up right back where they started. They haven't been displaced at all.
All right, next on our list is speed, another one you know well. It's just how fast something is moving. The formula is super straightforward. You just take the distance traveled and divide it by the time it took. That's it.
But this is where our new language has to get way more specific. You might think velocity is just a fancy word for speed, but it is absolutely not. Velocity is speed plus a specific direction. And if you look at the formula, you'll see it uses displacement, not distance. That's a huge clue. It tells you that direction is baked right into the very idea of velocity.
Let's bring back our track runner to really see what this means. So imagine they're running at a perfectly steady pace, let's say 5 meters per second. Their speed? Totally constant. But is their velocity constant? No way! Think about it. They're running in a circle, which means their direction is changing every single moment. And if the direction is changing, the velocity has to be changing too, even if the number on the speedometer stays exactly the same.
And that idea leads us perfectly to our final key term, acceleration. Now, in everyday life, when you hear acceleration, you probably think of hitting the gas pedal in a car, right? Just speeding up. But in physics, it's so much more. It's any change in velocity. And since we just learned that velocity includes direction, well, that means you can accelerate in a few different ways.
So here's the big takeaway. You ready? An object is accelerating if it's speeding up, if it's slowing down, which we sometimes call deceleration, or if it's just changing direction. So that runner on the track, the one with the constant speed, yep, they are accelerating the entire time because their direction is always changing.
All right, so now we've got our basic vocabulary down. So how do we use these words to, tell a story about motion? Well, the most powerful tool we have for that is the graph. A simple graph can literally show you the entire story of an object's trip, all in one quick look.
Okay, let's start with the first type, the distance time graph. It's pretty much what it sounds like, right? The vertical axis, the y-axis, shows how far you are from where you started. And the horizontal axis, the x-axis, just shows time passing by. It's perfect for tracking where something is during its journey.
So reading these graphs is actually pretty intuitive. If you see a totally flat, horizontal line, what do you think that means? Well, it means time is ticking by, but the distance isn't changing at all. So the object must be sitting still. It's at rest.
Okay, so what if the line is straight but it's sloped? This means that for every second that passes, the object covers the same amount of distance. In other words, it's moving at a constant speed. And here's the real magic trick. The steepness of that line, what mathematicians call the slope or the gradient,
is the speed. Think about it. Slope is just rise over run. On this graph, that's the change in distance divided by the change in time. That is the literal formula for speed. So cool.
All right, let's switch gears now and look at our second main type of graph, the speed-time graph. Now, this one isn't telling us where an object is. Instead, it tells us how fast it's going at any given moment.
So the lines on this graph tell a totally different story. A flat horizontal line doesn't mean at rest anymore. Here, it means the speed isn't changing. It's constant. A straight line sloping up, that means the speed is increasing at a nice, steady rate. That's constant acceleration. And you can probably guess a straight line sloping down means constant deceleration or slowing down at a steady rate. So you see the pattern here? Just like the slope of a distance-time graph told us the speed, the slope of a speed-time graph tells you the acceleration. And the logic is exactly the same. Slope is rise over run. On this graph, that's change in speed divided by change in time, which is the exact definition of acceleration.
But wait, there's more. Seriously, there is even more information hiding in these graphs. Let's pull everything together now and see how we can squeeze out even more insights and even do some real calculations.
Okay, this is the other huge secret of the speed-time graph. We know the slope tells you the acceleration, but the area underneath the line, that tells you something completely different. It tells you the total distance the object traveled. Just think about it for a sec. How do you find the area of a rectangle? Length times width, right? Well, on this graph, that would be time multiplied by speed. And what does that equal? Distance.
So let's put this into practice. Imagine a car. It's starting from a dead stop, and in 5 seconds, it gets up to 10 meters per second. So to find its acceleration, we grab our formula. Acceleration is the change in velocity divided by time. Then we just plug in the numbers. That's our final velocity, 10, minus our starting velocity, which was 0, and we divide the whole thing by the 5 seconds it took.
And what do we get? We get our answer, 2 meters per second squared. But what does that number actually mean? It means that for every single second that goes by, the car's speed is increasing by another 2 meters per second. First second, it's at 2, second it's at 4, and so on. You see how this language lets us be so incredibly precise? Okay, so let's wrap this up with the key takeaways. First, the biggest trip up for most people is that tiny but crucial difference between speed, just how fast, and velocity, how fast and in what direction. Next, when you're looking at graphs, you have to remember the slope and the area underneath the line are telling you two totally different stories. And this isn't just some abstract thing for a test. This is used everywhere. Sports scientists use it to analyze an athlete's performance, and engineers rely on this to design things like safer cars, looking at acceleration data from crash tests to build better airbags. So we've spent all this time learning how to describe motion. We've been focused on the how, but that leaves one giant obvious question hanging in the air. We know exactly how to describe acceleration now, but what actually causes it? What's the push or the pull that makes something speed up, slow down, or turn a corner in the first place? That, my friends, is the next big piece of the physics puzzle.